not all elements form in an event like this one. Different nebulae tell different stories about their origins. Although some stars, like some people, live alone, most live out their lives with companions. The majority of stars reside in pairs, and these binary systems can lead to different types of extreme events. These binary white dwarfs are the cores of stars that used up most of their nuclear fuel. Each is about the size of Earth, but hundreds of thousands of times more massive. Left alone, a white dwarf will slowly fade away, but interaction with a companion can disrupt it violently, and it explodes. New elements formed during the explosion get blasted into space. In less than a minute, the explosion grows larger than our own sun. After a day or so, the growing remnant is larger than our solar system. The explosion has released atoms that are highly unstable. These atoms can transform into different elements altogether, releasing a tremendous amount of light and energy. We call this process radioactive decay. The nebula formed by this type of explosion spreads these newly formed elements out into space. It is especially rich in iron and nickel, as well as silicon and other elements. That's good news for us. Iron and nickel help make our planet habitable. Astronomers observe these nebulae in X-rays as well, detecting emission from specific elements. Let's return to Earth to see what this means for us. Our Milky Way galaxy is home to hundreds of billions of stars, and so vast that light, the fastest thing in the universe, takes nearly 100,000 years to cross from one side to the other. Astronomers have identified the remains of many supernovae, once formed by collapsing giant stars, as well as exploding white dwarfs. These are evidence of the generations of stars that have come before us. Each of these stellar ancestors has dispersed elements into the cosmos, giving us the building blocks of planets and life. We can see the orbits of the planets in the solar system now. And we're heading toward Earth, where we can search for elements that give us a habitable world. When we look at our home world, the most obvious sight is the water. In our oceans, ice caps, and clouds. H2O, formed from hydrogen that has existed since the beginning of the universe, and from oxygen, forged inside giant stars. We can also see land masses, green with carbon-based plants. The continents appear in a familiar configuration now, but they creep slowly around our planet. Movement powered by plate tectonics, a critical driver of evolution on our planet. If we could look inside Earth, we'd see that the continents float atop a mantle rich in silicon compounds. Deeper inside, we'd find iron and nickel, making up a liquid outer core and a solid inner core. But our planet would have cooled off and solidified entirely if it weren't for heat released by the decay of radioactive elements, including thorium and uranium. Warmth from these decaying atoms drives plate tectonics, And the interaction between Earth's solid inner core and its liquid outer core powers a magnetic field that shields our planet from harsh radiation. Without this protection, our oceans would boil away, and our atmosphere would evaporate into space. These secret ingredients make Earth a living world. Thorium and uranium are two of the heaviest naturally occurring elements, and they require the most energetic of explosions to form: the collision of neutron stars. We have frozen time to get a good look at this neutron star. About the size of a city, this ultra-dense stellar core is so massive and compact that its gravity warps space and time, bending light around it. And this neutron star has a companion, another neutron star. Both formed in explosions like the one at the beginning of the show, and both bend nearby light, including from each other. Like the pair of white dwarfs we saw earlier, these two neutron stars are spiraling together in a gravitational dance. We can unfreeze time to watch events transpire 200 times more slowly than in reality. As these objects grow closer, they send out ripples in the fabric of space-time, measurable by scientists in the form of gravitational waves. We'll slow time down a bit more as the neutron stars come in contact and release a burst of high-energy gamma rays. Material flows outward in long tails, streaming away from the merging stars. The violent collision of these two neutron stars reconfigures matter to produce rare, heavy elements, including uranium and thorium. These atoms have nuclei rich in extra neutrons, ideal isotopes for radioactive decay. This is also where we get most of our silver, platinum, and gold. If we add the elements formed in supernovae, the collapsing giant stars, and the exploding white dwarfs, we can see some are still missing. Not every element requires an explosion to form, such as carbon, the foundation for life. This element forms primarily in stars like the Sun. This enormous star is larger than the inner solar system, but it used to be the size of our Sun. Such stars grow into giants, but they die with a whimper, not a bang. This giant star is engulfing its much smaller companion, a white dwarf the size of Earth. If we speed up time so years pass by in seconds, we can watch as the gravitational pull of the smaller star steers up the gas flowing away from the giant. This accelerates material and eventually shapes it into a nebula, expanding gently into space. If we fast forward hundreds of years, we can see gargantuan bubbles of gas sculpted by the interaction between the giant star and its companion. Farther from the star, we see shells of material released in waves as it shed its outer layers. Energized by radiation from the hot white dwarf at the center of the nebula, individual atoms glow with distinct energies. Our telescopes detect this glow as different colors of light. It's rich in carbon and nitrogen, as well as some heavier elements. we see hundreds of these nebulae near us, along with the remains of the exploded stars we encountered earlier. Stars may die in these spectacular events, but they also spark life. New generations of stars enriched in the atoms that make up each of us. Over billions of years, these events have seeded our galaxy with the elements to form potentially habitable planets. New stars and planets continue to form in our galaxy. These locations mark stellar birthplaces, where enriched gas is giving rise to new generations of stars, most of which have families of planets in orbit around them. Our solar system was born in a similar way. If we turn back the clock nearly 5 billion years ago, when our solar system was taking shape, the galaxy would look quite different. Its atoms formed in more than 100 million events, like those we have seen during our journey so far. Material from our stellar ancestors had mixed through the entire galaxy. If the solar system formed here, we could track its elemental composition even farther back in time. These lines trace our atoms to their origins. Rewinding the clock, we can follow these paths to the supernovae, colliding neutron stars and dying giants that exhale elements into the cosmos. These are the branches of our elemental family tree. In this computer simulation, time is accelerated so that 20 million years passes by every second, taking us farther and farther back in time to where these elements formed. Our origins span the entire galaxy and beyond. The atoms in our planet and in ourselves were forged across hundreds of thousands of light years within an incredible volume of space in which individual diverse events contributed to create us here, now. We can trace our shared elemental ancestry to the beginning of the universe, through generations of stars that forged the atoms we now find on Earth. Elements that give us a habitable planet and the building blocks of life itself. The atoms inside each of us originated across unimaginable distances in space and time. We are the universe seeing itself.